Great. So I guess I'll just get started. My name is Michael, and I'll be giving a talk today on large language models or LLMs in healthcare. Really appreciate the chance to come and talk, and thank you so much for taking the time to listen to me today. So just as a little bit of background on myself, so my name is Michael. As I mentioned, I'm a fourth year computer science PhD student here at Stanford, co-advised by Nigam Shah and Chris Ray. And the focus of my PhD so far has been on developing foundation models for healthcare applications with a specific emphasis on deployment. So, not just doing research, but trying to translate that research into the hospital setting so that it can actually improve patient outcomes and hospital operations. For the talk today, we'll be focused on one specific type of foundation model, large language models. And the outline will be as follows. And also, if you have any questions during the talk, please feel free to add your questions in the Zoom chat or speak up. First, we'll start with the motivation. What are large language models and why should we care, especially in the clinical setting? Next, after kind of motivating why large language models are useful, I'll give an overview of kind of the current landscape of large language models for clinical applications. And so this is mostly based on a paper that we released last year called The Shaky Foundations of Clinical Language Models. After we kind of get a sense of the current landscape of large language models for clinical use cases. Next, I'll talk about one specific application that we looked at here at Stanford, which is matching patients to clinical trials using large language models. And this was also based on a paper that we put out earlier this year. And then finally, I'll talk about some extensions. So most of the talk will be about clinical language models, which obviously work on text as their modality. But there's also a lot of other data in the EHR, such as structured data. And so I'll conclude the talk with a few remarks on how we might think about modeling that structured data. And that's based on another paper that we put out last year called Earshot, a few-shot benchmark for EHR foundation models. Great. So with that, I will start with the first part of this talk, which is what are we talking about and why should you care? So to start with, what is a large language model, right? So a large language model, in the simplest way to describe it, is basically a machine learning model that takes text as input and outputs text. And that's basically it. It's that simple. So as you can see in the diagram here, on the left-hand side, this large language model is ingesting text, so like English, otherwise known as natural language. And on the right-hand side, the model outputs text in response. So basically, you can just think of it as a function that takes as input text and outputs text. And obviously, there's a lot of complexity that goes into engineering these models since at this point, if you've heard of models or used models like ChatGPT or Gemini from Google or Anthropic's Claude, these models have hundreds and billions of parameters and are trained on, internet scale data. So, terabytes and terabytes of text. And it's through this that they get a lot of the cool benefits that I'll talk about in a second. So this slide gives an overview of some of the various tasks that ChatGPT can do out of the box. And the main insight here is that because these language models are trained on language, anything that you can express in language, any task you can express in language, the model can basically attempt to complete, right? Because it just takes as input language and outputs language. And so anything that you can express basically in language, the language model could potentially be well suited to solve. And so that's kind of the key, one of the main pieces of magic that comes out of these models is that they can basically be applied to a broad range of tasks out of the box, even if they haven't been specifically trained to do those tasks, right? So as an example, this is just straight from the ChatGPT website, but even though this model was trained to essentially predict just the next word in a sentence on a bunch of data scraped from the internet. So the way these models are trained, it's basically like an advanced autocomplete. It's literally just what is the next word in the sentence? Can the model predict that? That's the whole training objective. From that, you get all these what are called emergent abilities. For example, you can use this model to correct your grammar and do spell checking. You can also have it, summarize articles. You can have it write code, write Python or SQL. You can have it write books and poems, all these tasks, just because we can express them in language. And the fact that these models are trained on just so much raw data means that they generalize to a very broad range of downstream applications. And so that's kind of the magic in these models that we're trying to bring into the healthcare setting. And so there were a lot of potential applications that we thought of last year when we started looking at these models and how they were starting to be applied in the clinical setting. And so I'll briefly run through 6 of the main high-level benefits that we see these large language models bringing to healthcare in contrast to traditional machine learning models. So the first one is probably the most obvious, and that's that these large language models can help us do better predictive performance on tasks that a hospital would care about. So here's an example from a paper out of NYU from last year where they basically trained a large language model on a bunch of clinical text. And here the large language model is the green bar and the traditional model is in gray. And as you can see for the 2 tasks that they were looking at, predicting mortality and readmission risk, the language model far exceeds the traditional machine learning model in terms of accuracy, right? And so immediately off the bat, you're seeing, hey, if all I care about is just I want the best model possible, I should think about a large language model because of its ability to process natural language and unstructured data within the clinical notes in the EHR. But that's just one of the possible benefits that we saw out of this model. And obviously, that's the one people are most focused on, but there's a lot of other ancillary benefits you get from working with these large language models. Another one is that they are more sample efficient. And so what I mean by that is it requires less training data to get them to equal that same performance that we just saw in that graph. And so I'll talk about this later in the talk, but basically we had a paper earlier this year where we basically did matching of patients to clinical trials in a 0-shot fashion. And by 0-shot, I mean that there's no training data, there's no examples we give the model to tell it, here's how to do the task. And so in a setting like healthcare, where labels are especially expensive and costly to curate, this less labeled data advantage is pretty significant. Since that's always a struggle whenever you're training these machine learning models. It's like, I need a doctor to label even more notes. With these language models, because they're more data efficient, that concern is mitigated. The third key benefit that we saw, which makes a really big impact when you start thinking about deployment into the health system, is that these large language models simplify model deployment significantly. And the reason for that is this one model, like I said on the previous slide, can do a ton of downstream tasks, the same base model. And so here you're seeing an excerpt from a recent paper from Google called MedGemini, where they use the same exact base model, and each grouping of bars is a different type of task, a different data set that they evaluated the model on. And so you see that the model achieves very strong performance across a wide range of downstream clinical medical tasks, even though it's just one base model, right? And so when you start thinking about, okay, how do I deploy this? The benefits that you get from the large language model based approach versus the traditional approach in which you're training a separate model for each task and you have to manage each separate model's endpoint and deployment and maintenance and all that sort of stuff. Now I'm just dealing with a single model, and the one model is able to do a bevy of downstream tasks. That greatly simplifies the burden on the IT infrastructure of a health system. And that's something that we're actually thinking about very heavily right now at Stanford as we start to deploy these models into practice. Deploying one model is much simpler than deploying 100. The fourth key benefit that we saw was what we called emergent clinical applications. And so basically, this is any application that would previously be beyond the realm of imagination when it came to machine learning. And so here's an example from a recent paper earlier this year where they used ChatGPT to basically translate, I think it was like discharge summaries or some patient-facing communication from clinical jargon to something that a normal person could actually understand, right? And that would have been something inconceivable even a few years ago. And so there's a ton of interesting applications that we have yet to quite imagine where these language models could lead to significantly improved performance and applications and entirely novel use cases that previously wouldn't have been possible. The fifth kind of interesting thread that we saw from some of these models lately is the multimodality angle that they're able to support. So as you can imagine, when a doctor looks at a patient, they're not just reading the previous physician's clinical note and not ever looking up from their screen, right? They might be reading an image at the same time. They might be looking at the patient. They might be having a conversation. They might be looking at the vitals. There's a lot of different modalities of data that a doctor would consider when making a diagnosis or a decision. And so our models probably would benefit from being able to reason over that data in the same way that a human would. And so this was a really cool paper called MedFlamingo that was published last year, where they basically did just that. They attached a vision model to a large language model, and they were able to have it reason over both text and imaging to make a response. And finally, the last key benefit that we saw coming out of these models, beyond just, they're more accurate, is the ability for humans to interact with them in novel ways. And so what I mean by that is, if you've ever used ChatGPT, right, it's not just like the model spits out an answer and then it's done. Instead, it's a dialogue with the user. So ChatGPT writes something, and then you're able to respond to it, and it's able to respond to your response, and so on and so on. So you can actually have a conversation with the model. And so here's an example of, I think what they were doing was they were generating synthetic chest X-ray images, where they basically told the model in English, hey, I want an image that has these properties. And then the model would be able to generate those images. And then you could kind of go back and forth and iterate until you had an image that you liked. And so there's just this whole universe of really cool human AI interfaces that I don't think we fully thought through, but are a very exciting opportunity for future research. And so these are, at a very high level, some of the main benefits that we saw from the perspective of, okay, we're a health system ready to deploy these things into practice. What are the benefits that we should be thinking about, and how should we be evaluating these models? So now that I've kind of given an overview of what large language models are and why we should care from the clinical perspective, I'll talk about, I'll zoom out a little bit and talk a little bit about the overall landscape of people developing these large language models for clinical use cases, and kind of where the field is today, given all the potential that I just spent the last 10 minutes talking to you about. So first thing to just quickly note is we use this term clinical language model, or CLAM for short, to describe large language models that are designed for or fine-tuned for clinical use cases, just to distinguish them from more general large language models. And so the focus of this section will be on CLAMs, or clinical language models specifically. And so basically, a clinical language model, all it does, it's just a language model for clinical tasks. It takes as input text, so medical or clinical or biomedically oriented text. For example, you might ask it, what medications is this patient taking? And then you might throw in a really long note. And then the CLAM processes it, and it outputs, natural language. So it'll say, hey, this patient is taking a statin for their hypertension. And so basically, it's just a large language model, but for clinical tasks. And there's, a bunch of these, obviously, there are popular general large language models like GPT-4 and ChatGPT, but there are also a number of language models specifically tuned for clinical tasks. For example, there's a sort of called Hippocratic AI that's doing it. Google has a couple versions like MedGemini and MedPalm. And then there have been some academic efforts, such as Gatortron out of the University of Florida. So for this paper that I'm going to run through, called The Shaky Foundations of Clinical Language Models, which we published last year, we looked at 50 different clinical language models in the literature. And so here's just kind of a brief summary of the different models we looked at. Basically, there's no reason to actually look at all 50 of these, because once you see enough of these, you kind of notice a pattern, and they're almost all basically follow this same template at their core. So this is how almost all of those CLAMs on the previous slide were created. So you start with, your randomly initialized, vanilla large language model, and you pre-train it on a bunch of data from the internet. So this is like Wikipedia, Reddit, news articles, books, just general language, right? Nothing specific to the clinical domain. And from that, you get your normal large language model. And this process is called pre-training. And so one of the more famous examples of this large language model is one called BERT. And so after you have your normal, just general purpose large language model, to turn it into what we would consider a clinical large language model, all you do is you take a corpus of clinical data. So two popular ones are PubMed articles, and the clinical notes from Mimic-3, the Mimic-3 data set. And then you do what's called fine tuning. So you basically continue to train your base large language model on this clinical data, and then out pops your clinical language model. And then usually the authors will give it a prefix like clinical or bio or med. And so from BERT, you get clinical BERT. And this pipeline is basically how all of these large language models are for clinical use cases are created. And so When you actually then kind of look at the data that these models are trained on, you get you start noticing a lot of patterns. And so here we've on the y-axis is the number of clinical language models that use each of these corpuses for their fine-tuning stage. And if you actually look at, okay, what corpuses are these, papers using? Basically, everyone's using the same two corpuses, right? It's PubMed and the notes from Mimic 3 or Mimic 4, right? And so even though on the previous slide I showed you, 50 different clinical language models, all with different names and features and whatever, if you really dig into it at their core, there's really not that much diversity in what's been put out there. And almost all of them basically recycle the same data, the same pipeline, et cetera. A model is basically an artifact of the data it's trained on. And so, there's a lot more similarity, I guess, in the field than you might perceive just looking at, the number of papers that are published. In terms of evaluations, we also looked at the different types of evaluations that these models were evaluated on, where here the columns are different large clinical language models, and the rows are evaluation tasks. The green highlight are clinical evaluation tasks. So for example, the named entity recognition task used as a data set, like a clinical note. And the blue rows are tasks based on biomedical literature. So here, the named entity recognition task might be based on, a bunch of articles from Nature or Science. Biomedical versus clinical text, just a slight difference. And so as you can see here, there's a lot of evaluating going on, but it's very scattershot, and there's not a lot of consistency in how these models are being evaluated, even within, the same clinical text or biomedical text universes. And so it's very hard to do a fair comparison of these different models. And even when you look at, what are the evaluations that people are doing, you'll find that most of the evaluations, almost all of them, are focused on only one of the purported benefits that large language models could bring to healthcare that I spent the previous slide discussing. So, almost all these language models are evaluated on, how well do we do on this predictive task, which, is a very important benefit that we need to validate. But from the perspective of a health system hoping to deploy these models, there's a lot of other potential benefits that we really aren't spending enough time thinking about or evaluating our models on, right? Like the sample efficiency, like how much labeled data do I need to apply these models to my task? Am I able to interact with these models in a way that allows for, that human AI collaboration? Does it simplify the deployment that I'm going to have to do, the cost and the maintenance burden? And as you can see from this chart, there just aren't that many papers focused on those sorts of evaluations. And so that was something that, we wanted to highlight as something that the field should ideally move a little bit more towards. The nice thing, the really big positive, which I'll conclude this section on, is that most of these language models are publicly available, often via a website called Hugging Face. And almost everyone publishes the full code and the full weights of their model so that other people can download and reproduce their results. So that is a really nice aspect of working in this field, is that there are a lot of great shared artifacts for people to work off of. So now that I've given kind of an overview of what is out there in the world of clinical large language models, I will spend the next part of this talk describing one specific application, which hopefully offers some generalizable lessons to folks interested in taking these clinical language models and applying it to their own clinical use case. And so this one will be about zero-shot clinical trial patient matching with large language models. So to kind of motivate the problem setting, the problem in a nutshell that we were trying to tackle in this project was that finding eligible patients for clinical trials is a very difficult process, as anyone who's worked on a clinical trial can vouch for. And so the stats are very alarming. So if you look at it at a macro level, almost a third of clinical trials fail because they simply can't enroll enough patients, right? And so this has nothing to do with if the drug's safe, if the drug's efficacious. It's simply an operational failure to get enough patients to enroll in your trial. And from the patient perspective, this is also extremely detrimental, especially in disease areas like cancer, where oftentimes the standard of care or the best treatment available the patients is in the form of a clinical trial. And yet, if you look at surveys of patients, roughly 94% of patients who might be eligible and interested in a clinical trial are never considered or informed by their doctor about trials for which they might be eligible. And so there's just this great, operational failure to connect patients with trials that they might benefit from participating in. And so why is this a problem? Why is recruitment so challenging for clinical trials? Well, if you kind of examine how it's done today, it's not really a surprise, unfortunately. So on the left-hand side, we have our clinical trial, right? And so this is a trial protocol that's been prepared by a pharma company, and it has a list of eligibility criteria, both inclusion and exclusion. Inclusion means you have to have the criteria to enroll in the trial. Exclusion means you cannot have an exclusion criteria, otherwise you're excluded from the trial. And so your clinical trial protocol will have roughly, 30, 40, or 50 of these bulleted eligibility criteria that every patient must meet to enroll in the trial, right? And these criteria can be simple, like the patient is over 18, but they can also be fairly complex, like, the patient has this mutation and they have a family history of X and Y, but they haven't had this drug in the past 3 months. And stuff like that. So there's like these interesting temporal components, there's clinical judgment involved. It's not trivial just to take these natural language descriptions of criteria and map them to what is the kind of query I should be thinking about in my head when I match patients. So on one hand, unstructured text, hard to parse, challenging. And on the other hand, you have the patient's health record, which is also full of unstructured text, full of clinical jargon that is hard to parse and difficult to understand unless you've been trained. And so the challenge then basically is, you have your patient's health record at a hospital and you have your trial protocol on the other side. And the job of a research coordinator, a clinical research coordinator, is to basically go through each patient's chart one at a time at Stanford Hospital or whoever's running the clinical trial and check, hey, does this patient match all of these criteria, right? And so basically you have a clinical research coordinator manually scrolling through each patient one at a time, reviewing hundreds or even thousands of records to try to find enough patients to enroll in these trials. And the reason why it's hard is roughly 80% of the relevant data for matching these patients to trials is hidden in the unstructured text within an EHR. And that makes automation very difficult because you can't just look at the structured information and run a SQL query over it. You really have to look through the notes and do that sort of natural language processing in order to understand, hey, this patient actually does meet these criteria, yes or no. And so if you actually look at the amount of time it takes per patient, it can range anywhere from 10 to 40 minutes to even I've seen quotes of an hour per patient for some complex cancer trials, just to check, does this one patient meet or not meet the eligibility criteria for this one trial, right? And so this is just an operational system that does not scale as it is today, but it's very hard to automate because a lot of the data is unstructured text. And so that motivated the application of large language models, right? I spent a lot of time talking about unstructured text, natural language. And so, the light bulb probably went off in your head. Hey, why don't we apply a large language model, which is specifically well suited for processing natural language to a task which has been hard to automate because there's so much language to process. And so that is exactly what the point of this project was. It was to try to automatically match patients to trials using large language models, and specifically to do it in a way to do it with an eye towards deployment. So to try to do it in a way that seems scalable. And I'll explain that in a little bit. So just to kind of level set, the data set that we used for this project was based on the 2018 N2C2 cohort selection benchmark, which is a publicly available data set of 86 patients with around 377 de-identified clinical notes associated with them, so roughly 4 notes per patient, and then 13 inclusion criteria. And the task is to basically predict whether each patient meets or does not meet each of those inclusion criteria. So this is not a real trial. It is a synthetic example. The patients, the notes are real. But the point of this was to create some sort of public benchmark so that it would be easy to compare models and see which approach is best. And if you're interested, you can also download this data set as well. And so just to kind of summarize what the exact task that we're doing is, basically you have clinical notes for your patient on the left-hand side, you have your inclusion criteria on the right-hand side. Both of these are specified in text. So, the clinical note, obviously that's text. Your inclusion criteria, there's some brief, one sentence definition associated, like, history of intra-abdominal surgery, blah, blah, blah. And then the task is basically you feed both of these pieces of text into a large language model and have the model output either yes, the patient meets the criteria, or no, they do not. And it's that simple. Basically, because both of these inputs are expressed via text, we can just feed them directly through the large language model and get an output, a yes or no output as well. And so to kind of cut to the chase, the result was that we were able to show that these large language models can accurately do this sort of matching between clinical trials and patients at a state-of-the-art level of performance. And most interestingly, do it in a zero-shot fashion. And again, by zero shot, I mean no training data, no labeled examples, purely out of the box, these models can perform this task. And so just to kind of zoom in on that specific result, here is a table where the top row is the prior state-of-the-art model. It was a rule-based system that a bunch of domain experts had handcrafted. And so as you can imagine, this took time. It took domain expertise to create this model. And it was very specific to the specific trial and patient cohort that they were looking at. So it would not readily generalize to other trials. You'd have to restart the process from scratch. So you have to create a whole new rule-based system for a new trial. And so on the bottom, you have GPT-4 out of the box. No fine-tuning, no rule-based systems. This is just GPT-4 trained on internet scale data, has never seen the clinical trial patient matching task before, completely zero shot. And so the surprising result was that, as you can see, each of these columns is a performance metric and higher is better. Out of the box, GPT-4 beats the prior rule-based state-of-the-art system across every performance metric that we were looking at. And so this tells us that it is more accurate at the patient matching task than prior models that experts had spent hours laboring over creating. And so just to explain each column, the leftmost metric is precision, which is basically of the patients I say who meet the criteria, how many actually meet it. Rec is recall. So of the patients who do meet the criteria, how many am I able to find and correctly say meet the criteria? And then macro F1 and micro F1 are just two different ways to average precision and recall to give like an overall sense of performance that balances the two. And so the key insight here is, not only are these large language models comparable or even better out of the box on this task, but they did it without any training data, right? Which means it can be reapplied to any trial with minimal reconfiguration. And so that's what got us really excited since, like I mentioned before, the focus of my PhD has really been on how do we get these systems into production and deployment. And so to kind of double click on what I just said and why that's important. So here was the original task we had, right? It's patient A, inclusion criteria X, feed these through the model, and then we get out a response. And to apply it to a different trial with different criteria, it's as simple as literally giving the definition of that criteria to the model. So now I have inclusion criteria Y, and now the model is assessing patient A against this different criteria because it's all expressed via text. And then if I want to apply it to a different patient, all I do is swap out the clinical note for a different patient, feed it through the model. And again, because it's text, the model can just ingest this with basically no reconfiguration necessary. And so that's how we see this scaling to arbitrary numbers of trials and patients. The other big consideration, though, is, okay, great, you have a system that works, but a very important thing to think about when you're actually building things for hospitals is, can they afford it, right? Is this within budget? What is the cost of actually deploying the system, even if, let's say, it's perfect, right? And so for this next part of the paper, we looked at the cost efficiency of using these models. So here we tried a bunch of different prompting strategies. Just to very quickly explain what's happening here. So on the left-hand side, under prompt strategy, there's two columns, criteria and notes. Under criteria, the word all means we feed all the criteria to the model at once. So all 13 criteria, we throw it at the model in a single input, and we have the model spit out predictions for all 13 criteria at once. If it says individual, then it means that we feed each criteria one at a time through the model. And so the model only has to think about one criteria at a time. And kind of the same deal with notes. All notes means all the patient's 4, 5, 6 notes, we feed it at the model through the model at the same time. Individual means we feed each note through the model once instead of all at once, right? And so In the middle columns, you have the same performance metrics on the previous slide. And, there are definitely differences. I won't say that the performances are identical, but, by and large, they're like fairly comparable, and it's not a huge difference in terms of performance. What is a huge difference, though, is the cost of these different approaches, right? And so from the top row to the bottom row, there's over an order of magnitude higher cost to be using one of these strategies over the other, even though their performance is roughly comparable, right? And the reason for that is some of these strategies require more API calls to the model, so more times that you're asking the model to respond. And they also use up more tokens. Tokens are basically just words. And so, because these models are priced on a per token basis, the more tokens you have the model input and output, the higher your cost is going to be. And so the takeaway here is, if you're a health system looking to deploy these systems, it's not sufficient just to look at accuracy. You may actually exist somewhere on an accuracy cost trade-off curve where you might not want the most accurate system because it will simply be impossible to deploy, but you can get roughly comparable performance at a much cheaper price, which actually makes it feasible to use for advancing, whatever care delivery mission that you're trying to advance. And so that kind of motivated the next part of the project, which was, okay, so we've tested throwing all the notes in at once. We've tested throwing each note individually. Is there a smarter way that we can only feed maybe the most relevant notes into the model and thereby reduce costs and retain as much accuracy as possible? And so here you're seeing the initial setup we had, where basically at the top in blue is the patient's health record. You can see there's a direct arrow straight into the prompt. The prompt is just the input you feed the model. So basically, we're just throwing notes into the prompt. At the bottom, you have in green the inclusion criteria we're looking at. Again, we're just pulling all the criteria, pulling all the notes, throwing it all into the model and seeing what happens, right? But shoving every note into the prompt, regardless of whether it contains relevant information for the specific criteria you're evaluating, is probably not the smartest thing to do, right? Like when a clinical research coordinator goes through a patient's chart, they're not going through every single note if there's hundreds or thousands of notes. Instead, they're using keywords, they're looking in familiar places. There's a smarter way you go about this, right? And so that motivated the next kind of technical contribution of the paper, which was to design what's known as a two-stage retrieval pipeline, or retrieval augmented generation, or RAG is another term you might hear, where instead of throwing all the notes in at once, we selectively pick out chunks or small subsections of the patient's EHR to feed in through the model, which we think are most relevant to the criteria being evaluated at that time. And so I won't get into a ton of detail here, but just to very quickly give an overview of the system. Basically, on the left-hand side near the scissors, we start by what's called chunking the health record into a bunch of small snippets of text. Then we do what's called embedding. We embed each of those chunks using a small language model to generate embeddings, which are basically just vectors. So think of it as like a 768 dimensional vector containing real numbers, where that vector represents in some machine understandable way the contents of that chunk. And then once you have those embeddings for each chunk, you store them in a vector database. You do the same thing for the criteria. So you run each criteria, which again is just text, through an embedding model to get out an embedding for each criteria. And then you do some sort of similarity search over your vector database to find for each criteria, what are the most similar embeddings of chunks in my patient's EHR. And then I'm only gonna return the top 3 or 5 or whatever chunks that match my criteria. And so the conclusion from this is that you can approach state-of-the-art performance using only a fraction of the tokens and cost as was described previously. And so here is 2 charts, both showing the same exact experiment. Nothing's changed from what I described before. The left-hand chart is just one metric, micro F1, and the right-hand chart is just another version of that metric called macro F1, which slightly upweights rarer classes. So if you care about rare criteria with low prevalence, you might prefer the chart on the right. But the same experiment, same models, same data set, same everything between these plots. The x-axis is the number of tokens that we're feeding through the model. So as you get farther to the right, we're just throwing more and more notes into the model. And then the stars on the far right-hand side are the performance of each model, where orange is GPT-4 and blue is GPT-3.5. When you feed in all the data at once. So we don't do retrieval, we just do what we did naively to start with, right? So that's kind of like the ceiling of performance. And the y-axis is the F1 performance metric, right? So higher is better. And then the last thing to signpost this plot is that the prior rule-based state-of-the-art method is the green dotted line at the top. And so the key takeaway from this plot, I mainly look at the GPT-4 orange curve, is that you can approach state-of-the-art performance with only a fraction of the tokens that you might otherwise think you need if you were doing the naive approach of throwing everything into the model, right? And so as you see, like in the macro F1 plot, you can exceed the state-of-the-art with roughly a fourth or a third as many tokens as you would need if you were throwing everything into the model at once, as long as you just, intelligently retrieved the proper chunks from the patient's EHR using that retrieval system. And the same story on the left, where you see that the performance gains of adding more and more tokens very quickly plateaus after a certain point, right? You still do see performance gains, but they're not quite as substantial as going from 1 million to 2 million tokens. Once you get to 5 or 6, the gains basically plateau. And so the key insight from this experiment was that if you're a decision maker in the healthcare space, you shouldn't be thinking about these models from just, is this more accurate? But rather, you should be thinking about these models on a continuum of trade-offs, where accuracy may trade off with cost or efficiency or some other metric that you care about, right? Nothing is ever isolated in a vacuum. There's always trade-offs. And so as you think about deployment, certain health systems might want to live on this cost versus accuracy curve at different places, right? Maybe, you really care about getting the most accurate patients for a rare disease trial, or maybe you're a health system with a bigger budget, or maybe, you're a community clinic and you don't have the resources to be spending thousands of dollars per trial, right? And the point here, though, is that for each of these health systems, there's a point on this curve that you can choose whatever best matches your own situation. And so that was kind of the other key takeaway from this work. Lastly, as we were thinking about, okay, how would you actually deploy this, right? Obviously, you would never just take at face value GPT-4's output of, hey, this patient's eligible, so let's inject them with a drug, right? There will always be a human in the loop. There should always be a research coordinator overseeing this process. The hope is just that this accelerates that screening process and helps avoid a lot of the, very easy non-qualifying patients, or the very easy ones that match, right? And so in order to do that sort of, human AI collaboration, the model needs to be able to output something in an interpretable fashion. And so this last experiment that I'll talk about from this paper was drilling into, how can we make this process interpretable to a human? And so originally this was our task, right? We had clinical notes from a patient on the left and inclusion criteria on the right. We fed that to a model, and the model said, hey, yes, this patient meets the criteria, or no, they don't. But because the model is just outputting natural language, if we just ask the model, hey, in addition to saying yes or no, can you also tell me why you made that decision? The model will gladly output a rationale justifying why it made that decision. So now, instead of just saying, yes, the patient meets the criteria, the model will try to explain, yes, the patient meets this criteria because they're taking these medications, and I saw this in the note, and the patient has this history, et cetera, right? And so now there's, some reasoning that, I can latch onto and verify, like, yes, I agree with this, or, there's something I should look into. And so what we did is we had GPT-4 generate these rationales for every matching it did. And then we subsampled, I think, roughly 400 or 500 of them. And we had 2 clinicians review these rationales and assess whether they were fully justified by the actual patient's EHR, partially justified, or incorrect. And so for eligibility decisions where GPT-4 made the correct decision, so GPT-4 either said, yes, the patient meets the criteria, and they did, or no, they don't meet the criteria, and the patient did not, we see that roughly 97% of the correct decisions that GPT-4 made were fully or partially justified, right? So that's the green bars here. And so that was a pleasant finding, because it seems like, okay, the justifications, the reasoning process that it's following to make these decisions, it's not just outputting a random number between 0 and 1, like there is legitimate justification behind these correct decisions. The more surprising finding was when we looked at decisions where, according to our data set, GPT-4 made the incorrect decision. And even in these settings, we found that, according to our clinician annotators, the natural language justifications, the rationales that GPT-4 provided, were either fully or partially justified 3/4 of the time, right? And so again, in the bar plot here, each row is a criteria, and each bar in green is correct, yellow is partially correct, and red is incorrect. And so this was very surprising. And I think there's, potentially two reasons for this. The first is, data sets aren't perfect. There could be mislabeling in the actual data set itself. So it could be the case that, this large language model made a decision that was correct, even though the data set was originally annotated incorrectly. But I think a larger and, more general takeaway from this is that there is a lot of space for legitimate clinical disagreement when it comes to a lot of these eligibility criteria, right? Like, what does it mean to have a severe cardiovascular event or a severe complication from diabetes, right? The term severe is not, it's not a precise term. And so clinicians can have legitimate disagreement when looking at the same patient over whether they meet a specific criteria or not. And so this actually, I think, speaks to one of the biggest benefits of using large language models for these sorts of tasks versus traditional machine learning models, because a traditional machine learning model would basically just, maybe output a 0 or a 1, right? Or some confidence score between 0 and 1. But, what does that mean? Like a patient to be 0 or a 1 as in qualifying or not qualifying? Like medicine is a lot messier than that. There's a lot more gray area between a 0 and a 1. But traditional machine learning models can't really get you there. And when they output a confidence score, it's like, how do I interpret that? But the great thing about these large language models is instead of just outputting, 0.65 confidence that he or she meets this criteria, they can actually explain, this is why I think this person meets criteria, yes or no. And, whether, you call that reasoning or not to, not to anthropomorphize the model necessarily, but as this experiment shows, like there is some sort of legitimate higher order logic occurring where these models are able to justify to a clinician why they made this decision. And again, the clinician may disagree with the decision, but the justification is rational. And so I think for a lot of these more difficult clinical tasks, to go back to the original slide of benefits of LLMs, the emergent clinical applications, the novel human AI interfaces, there were a lot of tasks that were out of the realm of possibility with traditional machine learning because you could never really capture that gray area, that subjectivity, that, clinician judgment, right? Where that's so much of medicine is defined by. But because we're dealing with language, which is how we communicate these ideas and get at those sorts of vague assessments, right? These language models offer an opportunity for us to start tackling those applications and use cases, right? And so while it may be impossible for me to give you a single number to describe whether this patient fulfills a specific criteria or not, if you give me a paragraph to explain it, I'm sure I could convey to you why I think this patient has a severe complication, even if you might not see it in the same health record. So I think kind of that language-based output is a very interesting medium for researchers to think about in terms of, how can I be as open-minded as possible and think as big as possible about the applications that these models could be good at. So with that, I will move into the last phase of the talk, which talks about the rest of the EHR. So I know we spent a lot of time talking about clinical text, and there's a ton more to talk about. And we spent a lot of time talking about large language models specifically. But as anyone who's worked in a health system appreciates, there's a ton of other non-text-based data that exists in an EHR. And specifically, there's a ton of structured data, right? Billing codes, procedure codes, basically anything that you can represent in a table. There's tons of that information in the EHR. And so why should we be ignoring that, right? And so in this next part, I'll talk about extending some of the thinking that we've been applying to large language models and clinical text to the domain of structured clinical data. And this is mostly based on a paper that we put out last year called Earshot. So just to kind of level set, with folks in the audience. When I say, an electronic health record, what I really want you to picture is not, the Epic interface, but in the most abstract sense, what is a health record of a patient? And as you can see in this really nice depiction from my advisor, Nigam, a patient's health record, a patient journey is really a timeline of events, of clinical events that happen to them, right? And so there's a lot of different events that could happen to them, right? Like claims, medications, procedures, notes are written, there's vital signs measured, but all these exist in some sort of chronological ordering, right? Like there's a disease trajectory over time, right? And so this is how we think about modeling this sort of structured data. And so the previous, 45 minutes of this talk, we're focused on a single one of these rows, right? Clinical notes, applying large language models to this one row. But there's a ton of other rows in this table, right? And so how do we take advantage of all of this structured data? And so the that kind of brings me to the question of this section, which is, how should we think about modeling all these other rows in the table? And the very brief, kind of one sentence answer is, why don't we just treat it like text and use all the same great methods that I just spent, 45 minutes talking about, and just reapply them to structured data and not have to reinvent the wheel. And then we can leverage, almost a decade plus of great natural language processing research and methods and use them, essentially for free. And so what do I mean by that? How does that actually work? So let's think about language and what does it mean to model language, right? So here's, a book, right? And there's a bunch of words in the book. Each word is, a distinct thing. So in the verbiage of, machine learning, we'd call each of these words a token. So there's a bunch of tokens and they're listed in a sequence and there's sentences, right? So there's some structure to these sequences. There's sentences, there's paragraphs, there's pages, there's chapters, there's books, right? So there's some sort of organization of these words, but at its core, all that language is a sequence of words, right? A sequence of words from left to right. And so if we go back to the patient timeline view that I shared in the previous slide from my advisor, we can think about structured data, the EHR, in a very similar way, right? But instead of words, now our unit of of measurement, our tokens, are things like billing codes, medications, things like ICD codes, CPT codes, SNOMED codes, LOINC codes, right? Instead of call me Ishmael, now it's ICD code A, medication B, et cetera, right? And so again, we just think of this as a sequence of words, but the language we're using is now the language of billing, right? Or structured EHRs. And we have kind of the analog of sentences. We have encounters and we have visits within a patient's health record. And then each of these is associated with, a date. There's some timestamp, so there's some temporal component to it. But basically at a high level, this is how state-of-the-art structured EHR models think about the world and how they process the structured data within the EHR. So basically, we're just drawing an analogy from natural language, and then we're just going to reapply the same exact models like transformers, if you're familiar with those, or recurrent neural networks or things like that. Basically, we're just going to reapply those straight to the EHR and get state-of-the-art performance in a lot of settings. So basically, again, what this looks like is the input to these structured EHR models, which I call femurs for foundation model for electronic medical records, just to separate them from clams and large language models. So we have structured data from the patient's medical history on the left-hand side. We feed it through a femur, and then on the output side, we get whatever you want to predict. So maybe mortality predictions, or this patient will get this disease in the next year. Basically, whatever you want to predict or do, we'll basically take the representations learned from the femur model and use it to do our downstream task, right? And it's the same exact deal with large language models. Instead of the downstream task being anything that you can think of with text, like writing code or writing poems, or writing books, now the applications are, prediction making in the healthcare setting. And as long as we can express the input as a timeline of a sequence of clinical events, we can basically apply these models to any sort of downstream task we can imagine with just a little bit of fine tuning. And so we do see this empirically. So quickly walking from left to right, in this paper from one of my lab mates, Ethan Steinberg, a couple of years ago, they showed that these femurs are not only more accurate, but also more data efficient, right? So that gets back to the first two benefits I talked about earlier on from our survey paper: better predictive performance and less labeled data. And so as you can see from this chart, the red line is the foundation model, and you can see that it's consistently beating all the other non-foundation model baselines at every level of number of labeled examples. And even with only 100 labeled examples, you're beating the baseline model's performance with thousands of labeled examples, right? And so the benefit of these foundation models is you get improved sample efficiency and predictive performance out of the box. And then I guess I'll quickly just mention on this last slide the training data behind these models. For large language models, I said it was like we scrape the entire internet and throw the entire internet into these models to train them. Here, the analog is I take every single health record in Stanford's electronic health record database. So, 3 million patients' health records. de-identified. And then I trained this foundation model on all 3 million records. And then in an unsupervised fashion, which means I don't label any of the data. And then because it's looking at so many patients, the hypothesis is it's just able to learn patterns of disease progression, and then be able to reapply those to new patients or new settings in a much more sample efficient way than models that haven't seen 3 million patients, right? And so the key here, the key insight here is all this pre-training on 3 million patient records, the stuff on the left-hand side, it's all unsupervised, just like with the large language model case, which means that we don't label any of the data that we use for pre-training these models. So we basically get 3 million patients worth of information into the head of the model for free, because the task that we set up is the same one that we did before with large language models. We tell the femur to predict the next code in the patient's timeline given all their previous codes. So it's literally the exact same training setup as the large language models. It's just we're doing it on a different vocabulary. The vocabulary now is billing codes, procedure codes, et cetera. So that's kind of right. The first couple benefits we saw: better sample efficiency, better predictive performance. In the middle, this is from the earshot paper that we put out, where we basically see across 15 different tasks that a single foundation model is better across the board on all those tasks and can be adapted to a diverse range of tasks than training a bespoke model for each of those use cases. And here the blue line is now the foundation model. And then finally, on the right-hand side, there were a couple papers last year that showed that not only are these foundation models, better on more tasks and require less labeled data, but they're also more robust to temporal and data distribution shifts, which is, very important in the health system setting when you have things like COVID, for example, or billing practices change, or, you change the way that you deliver care. There's always huge shifts, even within the same hospital, let alone, trying to transfer your model to different sites or different health systems. And so, the fact that these foundation models, like I mentioned before, are trained on millions of patient records to start with, makes them more robust to those sorts of transfers. So the last thing I'll leave you with is just a shameless plug for one of the works that we put out last year, which is this paper called Earshot, which was the first EHR data set with longitudinal health records for the few shot evaluation of femurs, of foundation models for electronic medical records. And so I would encourage you to check it out. We'll hopefully be releasing the full data set publicly soon. And we also have a code for reproducing the results in the paper. And it contains roughly 7,000 de-identified longitudinal patient records, which is pretty unique, since almost every other benchmark and data set for electronic health record data that's out there today is only really focused on the emergency department or the ICU. And so this is a pretty unique artifact in that we have longitudinal health records of patients over long periods of time. And then in addition to releasing the data set and the benchmark, the other cool thing that we were able to do was release the full weights of our pre-trained femur model called Climber T-Base, which is now on Hugging Face. And so as you can see from the chart on the right-hand side, unlike clinical language models, which are very publicly available, femurs are, for some reason, I'm not sure why, people just don't like actually publishing them, which makes it basically impossible to reproduce results or to try to reuse a model for your own use case. And so we were very excited to be the first to put out the pre-trained weights of one of these models on Hugging Face so that anyone can download them. I'll note that the model is trained on OMOP CDM structured data, OMOP. So if your data set is structured or is ETL'd into OMOP, the model should work out of the box. Otherwise, you'll probably need to transform your data into the OMOP standard in order to work with this model. But yeah, please check it out if you're interested in building on this and fine-tuning it for your use case. And so yeah, so that kind of concludes the talk. Obviously, would like to take a second before questions to thank all my collaborators in both the Shaw and Ray labs and beyond. Thank my funding sources, the NSF and Stanford Healthcare. And then I'll leave you with links to the 3 papers I talked about. So the first one was the survey of clinical large language models at the bottom. The second one was the zero-shot clinical trial matching paper, which is actually at the top. And then last but not least, the Earshot benchmark, which can be found at this link. And we'd love to, have folks download it and try out the data set and see what they can build on top of the foundation model that we release. So thank you so much for the time. Really appreciate it. And yeah, happy to take any questions.